Hello, welcome to another lesson of sectoral structures theory. We are still continuing with the same chapter from the book. We are in chapter 5. Today we want to talk about characteristic sets, which is a very important concept in sectoral sets. Let's say we have a complete sectoral set, let's say ST4. ST4 has 6 elements or 6 sectoral structures, and therefore we say that Meem of 4 is equal to 6. Now, of those sectoral structures, 2 of them are reducible, meaning that if we do the dal function of these 2, we will get a sectoral structure of a smaller degree. So the 4 subscript 4 or the theta structure reduces to 1, 1. And then 2 squared subscript 4 reduces to 1 squared 2. And therefore, these 2 are reducible sectoral structures. And we say that the reducible set or the reducible subset of degree 4 T rho subscript 4 is equal to 4 subscript 4 2 squared subscript 4. And we will also say that rho of 4 is equal to 2 in sectoral structures theory. Now, we are left with 4 irreducible sectoral structures. And we will see that for any sectoral set, these irreducible structures are what define this particular sectoral set. So we will call these 4 the characteristic, we'll call it the characteristic set or the characteristic subset of degree 4. We will use the number chi or the letter chi. So we'll say T chi subscript 4 is equal to 3 1 subscript 4, 1 2 1 subscript 4, 2 1 squared subscript 4, 1 to the 4th subscript 4. And here we can see, if we think about what we're talking about, we will start seeing why there's a natural connection between sectoral structures theory and numbers theory. So we're really defining what structures are unique in ST4 and which ones have an isomorphism in lower degrees. Now, you can have isomorphisms in higher degrees for anything, but you can't always have the dal function reducing to a different sectoral structure. So we'll say chi of 4 is equal to 4. Of course, notice that Meem of n is equal to rho of n plus chi of n for any sectoral structure. Now, if n or the degree is a prime number, no matter how big this sectoral set is. So for example, if the degree is 10, then you're going to have a very large number of sectoral structures. But if it's a prime number, such as 7 or 11, you'll still have a very large number. However, we can say that rho of n will be equal to 1 if it is a prime number. So rho of 17, without having to draw out all the structures, we can say that rho of 17 is equal to 1 because there will be only one reducible sectoral structure in that set, and that is the theta structure. And I hope here we start seeing how sectoral structures are really the geometry of numbers. So we're looking at numbers in a geometric manner. We can also say that chi of n for a prime degree will be equal to Meem of n minus 1. Now let's do a few more observations. If n is a power of a prime number. So let's say we have the set, let's say n is equal to 9. Then that's 3 squared. That's the power of a prime number. We will notice in that case that row of n, or row of 9, will be equal to 3. In other words, row of n, or the size of the reducible structures in n, will be equal to meem of 3. So let's write this out. So let's say we have a is a prime number. Then we will say that row of a to the power of k will be equal to meem of a to the k minus 1. And please see the book for a little bit more information. But this is a very interesting relationship. I don't feel we focused on it enough in the book, maybe in a later publication. But this is a very profound connection here that we can see. And it is because, we establish a direct isomorphism, sectoral isomorphism, between the reducible elements of this larger set and the the entire set of n minus 1 or k minus 1. So let's, for example, look at the set ST8. ST8 will have a large number of sectoral structures. I'm gonna cheat off my table here. It will have 72 sectoral structures. So meem of 8 is equal to 72. Now, if we're only concerned with the reducible sectoral structures, then we really want the sectoral structures that are factors, or that are isomorphic to factors of 8. So this will include the elements of ST2. It will also include, or let's say this way, ST2. But it will also include all the elements of ST4. Now again, these are not the same elements, these are isomorphisms. But notice that ST2 is a subset of, or the elements that are isomorphic to ST2 are a subset of the elements of ST4. So really, we're only concerned with the highest power in this case. And that will be, here we have 2 to the 3. Here this will be equal to, so this 8 is 2 to the 3rd. We will say that row of 2 to the 3rd is equal to meem of 2 squared, which is meem of 4, which is, what is meem of 4? That is equal to 6. Okay? So this is the first relationship that you can see. I think the diagrams in the book are helpful, but perhaps in the next edition we need more explanation. The other relationship we want to look at is if n is a product of two prime numbers, let's say a1 and a2, such that they are both prime. We will notice that row of n in this case, or we will say row of a1 times a2, is equal to meem of a1 plus meem of a2 minus 1. And again, let's draw a diagram here. And we're only concerned with prime numbers. So let's say we have, let's say n is equal to 10. That is the product of two primes. We have this set here that is isomorphic to SC2. And we have another set here that is isomorphic to SC5. And the -1 is because we have the theta structure in common between these two. So we can see why rho of 10 is equal to meem of 2 plus meem of 5 minus 1. Now, if we start using more factors, we can still use these circle diagrams. However, we have to really be careful when we're doing it because it's easy to get confused. You'll see in the book, the images sometimes get really intricate. But if you're able to follow them, you can still figure this out using this method. But of course, we need a more reliable method. We will find, we will begin by focusing on the chi of n, because that's the characteristic set. So we will notice that chi of n follows a very clear pattern in this case. We will say it is equal to the sum of the Möbius function of d. So Möbius, the Möbius function of d times meem of n over d. So what is d? D are all the divisors of n. And n, of course, is the degree that we're concerned about. So this will be the sum of the Möbius function of d, or of the divisor, times meem of n over the divisor. The Möbius function, again, it's an arithmetic function from number theory. If n is equal to 1, the Möbius function is equal to 1. If n is a product of distinct primes, let's say 3 distinct primes, then we say the Möbius function is equal to -1 to the power of 3, so the number of distinct primes. And if n is equal to the square of a prime, then n becomes 0. Okay? So let's see, and this goes back to maybe why we started seeing some of these relationships arising when we have distinct primes. So let's do an example. That's the easiest way to really understand what's going on. Let's, for example, look at the ones we saw here. Let's do chi of 4, because we've already drawn the images out. Chi of 4 should be equal to, let me change the pen, the sum, this is better, of d over 4 for mu of d times meem of 4 over d. So that equals to, we're going to do this summation. We start with 1. So where mu of 1, or the Möbius function of 1, is equal to 1. So there is 1 times meem of 4 divided by 1 is 4. plus, let's look at the next one, 2. So 2 is made up of uh, one prime number, so that's the power of 1. Negative 1 to the power of 1 is negative 1. So we'll say minus mean of 4 divided by 2 is 2. What other factors do we have? We also have 4 itself as a factor. However, the Möbius of 4 is equal to 0 because it's a square. So plus 0. Meem of 4 is equal to 6 minus 2 is equal to 4. And this is indeed what we have here. Now, let's look at row of 4. So now we looked at chi, which is the characteristic set, which is really the more important one. But we can also derive row of n. We will say that row of n, as we know, is equal to meem of n minus chi of n, which is equal to meem of n minus this formula right here, which we just saw earlier. Again, this formula for the characteristic sectoral set is very important in mathematics. You will see it in some applications of the zeta function, lattice structures, signal processing. So you see it appear a lot in math and physics. Okay, let's continue. So we notice that for whenever d is equal to 1, so the divisor is equal to 1, we know that mu of 1 is equal to 1. And therefore, we know this can be removed or simplified. Mu of 1 times meem of n over 1 is equal to 1 times meem of n is equal to meem of n. Now here I want to point out a very small error in the text that we'll hopefully correct next time. So we can take the meem of n out of the summation and then just include here d does not equal to 1. I put d does not equal to n. It should be d does not equal to 1. So this way, we simplify it to the following. We say row of n equals to meem of n minus meem of n plus this summation, adding the condition that d does not equal to 1. And then meem of n and meem of n go with each other, and we are left with this formula. Row of n equals negative the sum of the Möbius of d times meem of n over d for all divisors of n except 1. So this is very interesting. We made a very small change to the formula, and we're going to end up with the two sets, the reducible set and the characteristic set. And here we're starting to see that the meem function really has a depth into number theory. So let's do an example for ST4. We will say row of 2 is equal to negative row of 4, mu of d times meem of 4 over d equals to negative, such as, forgot to add it again, d does not equal to 1. So let's look at the factors of 4. It cannot equal to 1, so we're skipping the 1. We're going to keep the negative sign. That's very important. We know meem. We know when the divisor is 2, we get mu. We got that earlier. Where was it? Mu of 2 times meem of 4 divided by 2 is 2. And we know this is negative 1. and Meem of 2 is equal to 2, so negative, negative 2. And then for the number 4, the divisor 4, the Möbius function is 0, so this becomes a 0. And this equals to negative, negative 2, which is equal to 2. And that is indeed 2 reducible sectoral structures. This is a very important lesson. It's a little bit difficult to follow if some of these concepts are new to you. But here we really start seeing the deep connections between sectoral structure theory and number theory, and as a result, with many other disciplines, including signal processing and others. Thank you.